In this video, we're going to start looking at some basic work with vectors in mechanics. Vectors are used in both 2D and 3D to model situations dealing with movement or forces. We're going to start off with recapping some basic terminology, notation and representation. So let's start off now with a coordinate axis. We could show now a vector with a directed line segment. So if I now draw a vector, this could be shown on a coordinate axis like so. So what we've got then now is our vector. Vectors have both magnitude and direction. So I'm showing the direction of this vector, and in a textbook you would see this bolded. If we write it, we put a little line underneath. In column form, we can see I've gone right 3 and up 1. So this vector will now be 3, 1. If I did a vector of the same size or magnitude as we say in the opposite direction, this would now be minus a. We're simply going now in the opposite direction. So we could write this now as minus a. And we can see that we're going left 3 and then we're going down 1. So with vectors we have both a magnitude, and the magnitude is simply now the length of this line and a direction. If we consider this is A, I could scale this up and say now that I had another vector, and this one is going to now be double the length, so that's going to give me 6, and then double the height. We could say now this is 2A. Later in the video we will look at scalar multiples, but we can now say this is 2A, and we can see that this is going across 6 and up 2. So this right here would now be the length. So we've got A and we've got 2A. Let's also look at some basics with now the vectors in terms of their geometrical properties. So what I'm going to do is just draw a triangle. What we're going to have is the following. We're going to have this point A, we'll have a point B, and we'll have a point C. So I'm going to label these up now A, B, C. So A is here, B is just here, and then C is just here. We will now say that the vector AB is A. We show this by writing A, B, and then a line above, and we say that this is going to be the vector A. This one right here, BC, I will say is going to be the vector B. BC is now the vector B. We can now say that the resultant vector is AC. By the triangle law, AC will be equal to AB plus now BC. And later again in this playlist or in the work, you will see that this is what we call a resultant vector. If you wanted to look at it on the coordinate axis, what we would have is the following. Let's say we've got something like so, and then something like that. Let's just do this. So what we'd have is just A, we'd have C just here, and let's write those on. So this now is going to be A, this will be B, this is going to be C. So if we look now at the vector AB, what we're going to have in column form, we've gone right 3 and down 2. So 3 minus 2. If we look now in column form at the vector BC, we've gone right 1 up 2. Now if I add AB, so if I do AB plus now BC, I'm going to end up now with 3 plus 1, which is 4. Then I'm going to have minus 2 plus 2, which is going to be 0. And we can quite clearly see that that is the resultant vector. We can see that AC is going to be equal to now 4, 0. We've gone right 4, and then we've moved up or down 0. As we move on through our mechanics module, we meet I and J notation. So let's get back to the coordinate axis. What I'm going to do now is draw the vector I. The vector I taken from the origin is of unit length. So its length is 1. So I, this is the vector I. It has a magnitude or length of 1. This is called the magnitude or the modulus. It's the absolute value. It's how long that line is. And this now is the vector I. It's in the x direction. If we now look at the vector J, that is going to be now in the y direction. So let's put that on and we can place that like so. So again, this is a unit vector. It has length 1 unit, and this now is J. So this point right here would be 3J. This point right here is going to now be 4i. This one over here is going to be minus 3i. This one down here is going to be minus 4j. So if I now travelled on a vector of 4i plus now 2j, what I'd have now is the following. Here is 4i, here is 2j. So that would be the point here. And we could represent it like so. And again, this might be metres, or we could write this in column form as 4-2. I prefer working in column form, but you have to appreciate both I and j notation and column form. If you're working in 3D, it will be I, j and k. The majority of this module and any module you'll do will work in 2D. As stated previously, a vector quantity has both direction and magnitude. A scalar will only have magnitude. What we're going to do is look at a couple of examples of vector quantities and their scalar equivalent. So let's go ahead and start with now displacement. What we've got now is displacement and its scalar equivalent, which is distance. So let's have a look now at an example of displacement. This now is the origin. When we talk about a position vector, this is relative to an origin. So if I place this point here, we can see now that this has a distance of 3. We would say the displacement is going to be 3i. This is a positive quantity. This also has a distance of 3 units from the origin, but it's got a displacement of minus 3i, whether that's meters, kilometers, or simply units. This now has a distance of 2 units from the origin, but we've got now a displacement of 2j. We've got a displacement of minus j. So the displacement knows both direction and now the magnitude. So let's look at an example. Let's say now I had the displacement vector, and we'll have a displacement vector, and I'm going to write this now in column form, and let's say that that's going to be, let's go for 3, 4. In I and j notation, 3i plus 4j. So that's its displacement. If we look at the distance is the absolute value, and we use Pythagoras to find this. So here's my displacement, right 3 and up 4. So what I'm going to do is just pitch up now a right angle triangle. So this now is going to be my right angle triangle like so. What I'm looking for now is the modulus, or now the absolute value of this length. We're looking for the magnitude, and that is the size of that vector. So if I put that on, what we're doing now is simply finding the hypotenuse of this right angle triangle. So this now is 3, this is 4, so we could say now, say this was vector A, let's write vector A, we could say the modulus, and we write it like so, is going to be equal to the square root of 3 squared plus 4 squared. So the modulus of A, or the magnitude, now the length of that vector, is going to be the square root of 25, which is going to give me 5, and that might be meters or units. So this is the displacement, this is the distance. That works exactly the same with speed. So let's look at some examples of velocity and speed. We're going to look at a range of velocity vectors. So let's write some down here. Let's look at some velocity vectors. Later on we'll see how these velocity vectors work. But for now, what we'll do is look at some in column form and then in some in I and j notation. So what we might have now is 3 minus 4, and that might be meters per second. We might have now minus 3i plus now 4j, and we'll do all of these in meters per second. Again, back in column form, we might have minus 4, and then we might have minus 3, and then finally we'll have now 4, and this will be meters per second, let's put meters per second, and then finally we'll have 4i plus 3j, and that again, meters per second. Now if we look at these as velocity vectors, and I'll start from the origin to make this nice and straightforward, we might have a ship that's travelling on a velocity vector of 3 minus 4. So we'd have a scalar multiple, and that would be time. So if we had now time was 1 hour, it would have moved right 3 and down 4. After 2 hours, it would have been 6 minus 8, and so on and so forth. Now, this is a velocity vector. Velocity is a vector quantity. It has both now direction and magnitude. Speed has only magnitude. Speed knows no direction, and we're going to see that here. So if I look at now moving on this velocity of 3 minus 4, that's going to put me just here, okay? So every hour I'm going to be moving in this direction. If we look at minus 3, 4, that's going to be just here. And we can now look at the next one, which is going to be minus 4, minus 3, which is going to be just here. And then the next one, what have we got? 4, 3, which is going to be just here. So what we can say now, these are all velocity vectors. If we consider the absolute value of these, that is the speed. So consider now this length right here of this vector. Consider this one just here. Consider this one, and then finally consider this one. What we can say is the following. Speed, which is a scalar quantity, speed is given to be now the absolute value, the modulus of the velocity. So again, if we look at these as simple right angle triangles, what we could say is the following. Let's grab that up. We've got now this right angle triangle. We've got this right angle triangle. We've got now another one, which is just going to be here. And then I've got another one, which is going to be there. If we look at all of these are going to all have now the same, let's just put that on a bit neater. These are all going to have the same magnitude. The speed of each is going to be the same. This is 3, this one is 4, this one is 3, that one is 4. They're all going to have now the square root of now 3 squared plus 4 squared. So these are moving now with speeds of 5 meters per second, each of them. This is going to be the square root of 25. This one is. So we can see now that if we're given a speed, we've got no idea which direction it's going in, but a velocity vector will. So this one is 4, 3, or if we like, 4i plus 3j meters. So generally what we'd have is some scalar multiple time here. So if we started at the origin, after 1 hour, t would be 1, we'd be here. After 2 hours, we would be at 8, 6, and so on. So this shows the difference now between a vector and a scalar. We can, of course, extend this to both 3D vectors and even use it with acceleration. In vector form, we can also consider the angle one of these vectors makes with either now the vector I or the vector j. So let's look at that in action. Let's grab up another grid. So let's say I put up another vector. Let's just draw a vector and we'll have this vector right here. So what we'll do, we'll go across 3. Let's go across 3 and then we'll go, in fact, we'll go across 4 and up 3. So make it nice and straightforward. So if we looked at this vector now, this vector which we place on, let's call this A. We can see now from here that A is going to be now, we've gone across 4 and then we've gone up 3. That now is the vector. We might be asked to state the angle that this makes with the vector I, and that's that angle there. So if we consider that this is 3 and this is 4, we can say now that the inverse tan of 3 over 4 will give us the angle that it makes with now the vector I. So in the I direction, let's just put that there, that is the angle that it's going to make. Remember, I is just simply now the unit vector that is parallel to the x-axis and sits there. So that's I. So in our calculator, we could work that out. So let's have a look at that, and checking it we're in degrees mode, we're going to take now the inverse tan of 3/4. So that tells me now that this vector makes an angle of 36.9, approximately 36.9 degrees. Yet if we merely had the speed of this now, or the distance of this, then we wouldn't be able to do it. And of course, if we consider the angle that that makes here, and if we call this now alpha, we can see that this value, we can say that alpha is going to be equal now to 90 minus theta. So the angle that it makes with the j direction, is going to be 90 minus that value. So you can see when we're working with vectors, we can also consider the angle. We're now going to move on and look at some basic questions with vectors. In later videos we'll put all of these skills together, but for now we just want to see some basic work. So we're going to look at a couple of questions and work through them. In this one we're asked to find the speed of a particle moving with a velocity of -2i plus 3j meters per second. So if we consider what this looks like, what we'd have if we took this from the origin, we're going to have minus 2, 3. So what we're going to do is come somewhere now up this direction. So what we're looking for then is the absolute value, the modulus. Now we're interested in the length of this. So what we can say then is the following. We can say speed is equal to the modulus now of velocity. So what we're going to have then is the speed will be equal to the square root of -2 squared plus now 3 squared. So that will give me a speed of now root 13, that's 4, that's 9, root 13 meters per second. And of course that is what we call an exact value. So if you want to put that through a calculator, you can get a decimal answer. I prefer to leave them in exact value, but if we wanted to give this now, for example, to 2 significant figures, it would now be 3.6 meters per second. So speed is the absolute value of velocity. It knows no direction. Okay, let's look at another typical question. In question 2, we're asked to find 1, the displacement, and 2, the distance moved by a particle with velocity 6 minus 1 meters per second for 5 seconds. Okay, if we consider this now, the displacement, what we're going to have if we just sketch this up, we're moving now with this particular vector. So we're going now 6 to the right and 1 down. So if we think about what's going to happen, that's going to go 6 across and then 1 down. We can look at this a couple of different ways. The displacement is simply going to be 5 times this. Every second we're moving here. So if we do that, what we're going to have then is 5 times by 6 minus 1, which is going to give us now 30. We're going to have 30 and then we're going to have minus 5. So that now is the displacement vector. So when we're looking for this, that is going to be in meters. So if you ask for displacement vector, that's what it is. If we wanted now the distance, what we could do here is simply now say that the distance is going to be the absolute value. So say if we said now that this was the vector A, we could say that the modulus was going to be now the square root of 30 squared plus minus 5 squared. Alternatively, what I could simply do now is find the value of this and multiply it up by 5. So I could have 5 lots now of 6 squared plus minus 1 squared. And that's going to give me now 5 root 37 meters. So that now is the distance covered. This is the displacement vector. This now is the distance. This second idea of representing it as 5 root 37 might help us later when we're looking at vectors of different magnitude in the direction of a given vector. So let's move on and look at another typical question. In part 3, we're asked to find the position vector of a particle after 4 seconds given, I think we should be given that at time t equals 0, the position vector is 3i plus 2j meters and the particle is moving with a constant velocity of 5i minus j meters per second. Okay, this is a new bit of learning here. We can say that r is equal to r0 plus vt. If we break this down, what it's saying is where I end up is where I started plus velocity multiplied now by time. This is our velocity vector. So if we just draw a quick sketch, and we'll just sketch this up, what we've got is the following. Let's say we start, and we're going to start now with a position vector at time 0, and that is going to be 3, 2. So let's put this on. So that's going to be now 3, 2. We're moving now with a constant velocity of 5i minus j. So what we're going to be doing is coming down in this direction. This is our velocity vector. So we'll see that we're going to be moving in this direction right here. So what we'll have then is the following. We will start here and then we will move 5 to the right and 1 down every second. So what we want to do is the following, and we can express this as we go. So we could, of course, count these. As t, though, gets big, we don't want to be doing that. So what we can say then is where we end up, which is r, is equal to r0, which is 3, 2. This is the position vector relative to the origin, plus now 4, that's t, multiplied now by my velocity vector. So what we've got then is the 5 minus 1. This is column form. I prefer working with column form, but you might be better off, if you like, working in INJ notation. So what we can see then is 3 plus 4 times by 5 is going to give me now 23. And then I've got 2 minus 4, which is going to be minus 2. So this is going to now be, we're asked for the position vector, that's going to be meters. So after 4 seconds, we're down here. Now later on in our work we will see that this has some really interesting consequences. So we might, for example, be given a ship, and let's write this here. Let's say we were given ship A, and we were told that this started with an initial position vector of 1, 2, and was moving with a velocity vector of, let's say, 1 minus 1. We might be given now ship B. We might be told that this has a position vector at the beginning of, let's say, 3 minus 1, and is moving on a velocity now of, and we might say, for example, this is going to be 2, 3. We could look to see if there was any time t where these collided. So we could say now that RA, the position of A, would be where it started, 2, plus the time multiplied by the velocity vector. So we could see at the time 0, it'd be 1, 2. Then if the time was 1 hour, and we were working in kilometres, we would now have this one right here, which would be 1, plus 1, which would be 2, and this one would be 1. And what we're going to see later on, and I'll just draw a quick sketch, we might see, and these are really quite rough, if we have 2 ships, we might see that they collide at some given point based on where they start and where they're moving. Remember, these ships are going to be moving, so it might be a case of where they were to intersect, they've actually moved past that. But later on we will look and see if we've got any values of t that will give us the same position. So just saying this one now, this is now the position of B, we'll just write this 3 minus 1 plus now t multiplied by 2, 3. So these now are position vectors, and this is something that you'll need to be able to work with. R is equal to R0 plus Vt. Where we end up is where we start, and then plus velocity multiplied by time. So let's move on and look at another type of question. In question 4, we're asked to find the position vector, I assume that's vector, of a ship after 3 hours, given its starting position is minus 2i plus 2j kilometres, and the ship is travelling at 10 kilometres an hour in the direction of 3i minus 4j kilometres an hour. Now, this is in the direction. If we consider now this as a vector, what we've got is the following. We've got 3i minus 4j. So if I now find the right angle triangle and get the hypotenuse of that, what we can actually see is the following. So if I move in now in this direction, what we've got is the following. That's 3 and that's minus 4. Now, if I consider the magnitude of this vector, let's just say that vector is going to be A. A is going to be now 3 minus 4. We know from Pythagoras that this is going to be 5. 3 squared plus 4 squared, or minus 4 squared, is 5. But this is moving now with 10 kilometres an hour. So one way we could do this is just to simply scale it up and have 2 lots of A, which is going to give me now 6 minus 8. So if now I've got this position vector, or vector as it says, we can say R will be equal to where we started, which is minus 2, 2, plus now what we're going to have is 10 kilometres an hour. So all I've done is scale this up. This now is in this direction. So it's going in this direction. It's going 3 minus 4, but at an increased speed. So I could say plus 3, and then instead of 3, 4, 3 minus 4, it's 6 minus 8. So 6 minus 8. So what we're going to end up with is the following. That's going to be now 16. 3 times 6 is 18 minus the 2. So that's going to be 16 minus 24 plus 2 minus 22. And that now would be meters. Or if you like, 16i minus 22j meters. So this time we're considering a velocity vector in the direction. Now this gives rise to something quite interesting. We can now introduce the idea of a unit vector, which we say is a hat. The unit vector is a now divided by its modulus. So if we consider what we've got here, a unit vector in this particular case would be as follows. We could say a hat was going to be equal to 1 over 5, that's the modulus, and then we would have now 3 minus 4. So, for example, if this question wasn't nice and straightforward and said that we're moving with 10 kilometers an hour, and I've just doubled it up, say it said we were moving in this direction with a speed, or we'll go for a speed, of 23 kilometers an hour in this direction, what I would do is simply multiply this up. So I could say now that r would be equal to minus 2 plus now 23 over 5 in this direction. So sometimes seeing this simply as a multiple is fine, and many questions you're going to get are going to be quite easy. It was only easy because essentially what I've done is scale this up. So this is actually moving as follows. This is coming down here, and that's going to be 6, and that's going to be minus 8. And we can see now by extending this line that I can make that into 10. But it might not be that easy, and that's where using the unit vector is going to help. The unit vector now is a vector in this direction but has a magnitude of 1. So essentially what I've done is made it now such that we've got this magnitude of 1, but it's going to keep you in that direction. So this now is how you find a unit vector in the direction. So for example, if you can't scale it up, just go ahead and do it. So for example now, if we had, let's say we had now, let's say that we had a speed now of 3 root 5 in the direction 1, 2, then this works out quite nicely. Let's just do this. Let's just draw this up. So we're going to go 1 and then we're going to go 2. So that's going to be 1, 2. So if I look at this as a right angle triangle, we've gone, and this is inaccurate, but hopefully it'll give you some idea, we've gone 1, 2. Now, if we use Pythagoras, 1 squared plus 2 squared square rooted is root 5. So if I'm moving in this direction with a speed of this, then all I need to do is consider I need to multiply this up. So that's going to be 3, 6, and then I could use that as my new velocity vector. Yet if it said that I was travelling with a speed of 15 in this direction, what I'd have to do now is 15 multiplied by 1 over root 5, which is the modulus, and then we'd have 1 and 2. So that's finding a unit vector in any given direction, and that can be really quite helpful. So there's some basic work now looking with direction vectors, velocity vectors, and going on to looking at a unit vector in any given direction. We can also consider basic work with the constant acceleration or SUVAT equations. So let's look at another question. We're told a particle has initial velocity 2, 3, so 2i plus 3j meters per second, and has constant acceleration minus 1 at 2 meters per second squared for 4 seconds. We need to 1, find the velocity, and 2, find the speed of the particle after 4 seconds. So let's go ahead and look at this. So what I'm going to do is write SUVAT just here. So if you haven't met SUVAT, please do go back and look at the videos on this. So what we've got then is an initial velocity, so that's 2, 3, and I like to write this in column form. Then we've got an acceleration, constant acceleration, so we can use these. So we've got minus 1, 2, and we've got a time of 4 seconds. So what we want to do is find the velocity. Well, we know from our previous work, v is equal to u plus at. So we can say now v is going to be equal to now the u, which is 2, 3, plus now the acceleration times by the time. So plus 4 lots of minus 1, 2. So what's that going to give me? My velocity vector now is going to be 2 minus 4, which is minus 2, and then that's going to give me 8. 8 plus 3 is 11. So we could say now that this is going to be minus 2i plus 11j, and that's going to be meters per second. So that is the velocity. Now we want to find the speed. So the speed now is the absolute value of the velocity, so it's the square root of minus 2 squared plus 11 squared. So what's that going to give me? That's going to give me now 4 plus 121. So the velocity is going to be the square root of 125. What's that? 5 root 5 meters per second. And of course you can just plug that into a calculator if you're asked to give it to, for example, 3 significant figures. So that's all we're doing. We're looking now at using the constant acceleration equations and going from there. Remember as well, acceleration is a vector as it has both magnitude and direction. So if we wanted now the magnitude of this acceleration, so let's say now the magnitude, and I'm going to say that this is going to be capital A for acceleration, thus not confusing it with the vector A we had before. The magnitude of this acceleration is going to be minus 1, and then we're going to have minus 1 squared plus 2 squared. So we could say now that the magnitude, now the absolute value of the acceleration is going to be, what's that, root 5 meters per second squared. So we can see now acceleration is to a vector quantity. We can see it's a product from here now, or I should say when we square root this, we will get a value here which gives the absolute value. So bit of work now with acceleration and velocity. When we're working with vectors, we can extend our work now to Newton's second law, or F is equal to ma. Force is equal to mass times acceleration. Force too is a vector as it's a product of mass and acceleration. Acceleration is a vector, therefore force is going to be now a vector quantity. So let's go ahead and look at a particular question, and we'll deal with this as well. So in question 6, a constant, I think this should be constant force. I don't know where these have come from. They're not incredibly well written. A constant force P acts on a particle of mass 3 kilograms for 5 seconds. Given initially the particle was at rest, and after 5 seconds the velocity was now 6.3 meters per second, find P and its magnitude. Okay, so let's go ahead. Let's go back to solve that now. So Newton's second law, NTL, let's just remind ourselves, NTL is equal to force now, or I should say NTL, force is equal to mass times acceleration. So if you're not cool with Newton's second law, you kind of need to understand this a little bit, but I'm thinking that you've done this before. So force is equal to mass times acceleration. Okay, so that's Newton's second law. So let's collect some information, and what we're going to do is use SUVAT. So we're looking for P, for force P, and its magnitude. Force is given in newtons, and again we can represent this in vector form. So what we'll have then is SUVAT. So back to our constant acceleration equations. So what we've got then is the initial. So initially it was at rest. So what we've got here is 0, 0. After 5 seconds now it was 6.3, and we can plug that in. And then we've got now, and we'll call this a little a for acceleration, and then we've got a time now. Time is 5 seconds. So what we can say then is v is equal to u plus at. So we can see from here that 6.3 will be equal now to u, which is going to be 0, 0, plus now 5a. So from here we can see that the acceleration is going to be, divide both sides by 5, 1.2, and then we're going to have 0.6, and that is going to be meters per second squared. So what we've got here now is the following. That is the acceleration. So we can say F is equal to ma, force is equal to mass times acceleration. So let's now put that in. So what we've got then is P. P is our force, and that's equal to the mass. Well, the mass is going to be 3, and we're going to multiply this by the acceleration, which is going to be 1.2, 0.6. So remember, that's going to be newtons. So we could say now the force P was going to be 3.6, and then we're going to have, what's that going to be, 1.8? 1.8 newtons. Or if we like, we could write this as 3.6i plus 1.8 j newtons. So that's a force. Now quite clearly the magnitude, the absolute value of P is going to be the square root of 3.6 squared plus 1.8 squared. And again, that'll be in newtons. So if we're asked for its magnitude, let's just work that out. So square root of 3.6 squared plus 1.8 squared. So what's that going to give me? 9 root 5 over 5, or 4.02, correct to 3 significant figures. So P is going to be equal to 0.02 newtons correct to 3 significant figures. Generally in mechanics modules you work to 2 or 3 significant figures depending on the question. So there we go, bit of work now using Newton's second law, force is equal to mass times acceleration, and we're simply plugging in values. So that concludes some basic work with vectors. In later videos we're going to explore this a bit more. That was just a brief intro on how we can use them. Lots of the questions we're going to do are going to be putting these skills together and looking at problems in context, whether that's a force acting on a particle, whether it's ships moving in a 2D plane, however we see this. Ultimately though, we're going to use these basic concepts and ideas to answer harder questions. So in the next video we will look at something that is slightly more taxing. Hopefully though that's been a good introduction to now vectors, position vectors, unit vectors, I and J notation, the magnitude of vectors, and also looking at some of their basic applications.